So our last speaker is Miguel, a research associate from the King's College in London. And you will do his presentation now.
Okay. Yes. Can you see me now? Yes. Cool. I'll start share my screen. Okay. Can you see my screen now?
Yes, we can see your screen. You
Okay.
are.
Yeah. Thank you very much, Marco, for this nice introduction. Yeah. So today I would like to speak a bit about my PhD work, essentially about nonlinear analysis to quantify human movement variability used from time series data. So the content essentially is why I'm interested in measuring movement variability, like the methods that we approach related to nonlinear methods, and one experiment, some results, and few conclusions. So why movement variability? So there are essentially a few challenges related to the quantification of movement variability, and I just classify these as three main challenges, which are theoretical, like choosing also the right tools for measuring such movement variability, and also technical challenges. So related to the theoretical challenges, so there are quite a lot of models to just modeling movement variability, considering tasks, environments, agents, or perception actions. So there's quite a lot of variables that can be used for modeling movement, human movement, as well as modeling human movement variability, such as complexity and predictability. Of course, there should be others that I may not know. Also, similar to these ones, there are different tools like time-based domain, frequency domain tools, or also perhaps nonlinear dynamics tools that may be able to measure this variability. And then from the side of technical challenges, there are also related to the type of data you have. You may have non-stationary data, which has some non-linearities. Then you may have also data length restrictions and the types of sources you use, and of course the different environmental noises that also may affect your measurements. So yeah, then just jumping into the different challenges for modeling movement variability. So we have this work of Newell. So, and basically he proposed to use these three variables, or which are related to the environment. So, for example, one person could be in the like the surgeon operating, or you can doing human robot interaction. So that will be the environment. So then the agent will be like a person where different factors like the gender, age, or health state will affect the way one person moves, and of course the activity that you may be performed in this environment. And therefore, then also related to this, you have like how you perceive this information and then how you move. To that leads to this concept of behavioral dynamics that sort of involves all these variables. So then I found the work of Staju. So he published this work where he put these two variables to model movement variability, and these are complexity and predictability. And he basically based his model on another work of Tononi, basically in the arrangements of neural networks. So based on the complexity and also the regularity of the neural networks, you can also have different like arrangements and structures of these neural networks. Similarly, with the movement variability, the complexity of this movement can be low, and when it's low and you have low predictability, you may have noisy and unstable behavior. But if you have, well, and then you have like more predictable behavior, but the complexity is low, then the movement may be modeled as rigid and repeatable behavior. Whereas the predictability is sort of in the middle, but the complexity of the movement is higher, then your behavior can be modeled as chaotic based behavior. And then that's basically how I start to get into more interested into these nonlinear analysis methods. So at the beginning, I was starting looking time-based methods, just like statistic analysis of average and standard deviation. Then I try also to do a bit of frequency analysis. But because of these problems I mentioned before, like the data length of the signals, or maybe they are very noisy, and also the types of source, because you may have like different types of sensors as well. All those changes impact the tools that you use to measure movement variability. And I found towards my journey in my PhD this method called uniform time delay embedding, which is based on Tucker's theorem. Basically, it is proposed to use two values, m and tau, to create a unknown dynamical system. And based on this, you also may have another way to represent the dynamical system using recurrence plots. And there's quite a lot of nice work for recurrence plots. But then also, when you find these patterns, you need to quantify. And the way to quantify these patterns is using something called recurrence quantification analysis. And with that, you have different metrics, like the numbers of black dots that you see in the recurrence plots, or the ratio between the black dots and dead values. Or also another important value for this work is the Shannon entropy value for the recurrence plots, which relates to the complexity measurements of the signal, which is based on the activities we ask participants to perform. And then I basically so I propose to use different values of dimensionality and tau, and also with this threshold as well from the recurrence plots, we can get different 3D Shannon entropy surfaces that will describe all these parameters for data length, different activities, and also different participants. And this is also another way to represent this 3D recurrence quantification analysis entropy. So let me show you one experiment that was performed 2 years ago during my PhD thesis. So I asked participants to wear an inertial sensor and then basically imitate what the robot did. Just very simplistic movements like vertical and horizontal movement. So they basically repeat what the robot does, and then I just measure the raw data from the inertial sensors from the participant and the robot as well. So what I'm going to show you here is different signal processing methods that apply to the time series from the inertial sensors. So for example, what you can see here is all these smooth signals. So basically, just quickly saying that the red one is for the human sensor, and the blue one is for the robot sensor. And what you can see here is like these sort of high frequencies for the movement of the motors. And then, of course, we don't want to measure that, so we get rid of these high frequencies using Savinsky-Golay filter as well to keep the structure of the time series. And we perform the same for the vertical movements. And so following the framework I showed you before, then apply minimum embedding parameters to get like m and tau, to then apply the reconstructed state space, which is this Tucker's theorem. So what you can see again, all these reconstructed state spaces. But then how we can measure that? So I did these recurrence plots, and I quantified the black dots that you see in each of these different horizontal normal, horizontal vertical, horizontal faster, and sorry, vertical faster as well. And so to then have these different like recurrence quantification analysis for four types of movements and two types of sensors, the human sensor and the robot sensor. And basically this plot is what is telling us is that the entropy measurements are more robust against each of the changes from different activities, which are like these four activities and two types of sensors. So that's what a good finding, because if we use rec, that or ratio, then some of these quantifiers doesn't show the differences between these activities or sensors as well. So so then we also found that this recurrence threshold also impact on the way we quantify these recurrence quantification analysis using Shannon entropy. So also we have like different values of smoothness as well to see how this impact the RQA entropy. And then the same for these different types of sensors different types of sensors, which are human sensor and robot sensor, and for activities as well. So we can now quantify these different variations of course of the length as well of the sensor as well. So using a window length of 100 samples to 750 samples as well. And of course, different participants as well. So we can also quantify this for like just showing here 3 participants from the sensor from the robot, from the person, and from the sensor from the robot as well. So nearly approaching the end. So there's three takeaway messages. So we found out that we can quantify this movement variability using nonlinear analysis, and then we found that the Shannon entropy seems to be robust against all these changes, and we test these different changes for types of structures of the signals, window length size, and also levels of smoothness. And then therefore we thought that Shannon entropy could be a potential tool to quantify the complexity of different movements as well. And there's still many things to do, like for example, investigate more about the methods to do a proper space reconstruction, because there's plenty of things to do for the the creation of these M and tau values. Like have a more robust value for entropy measurements with recurrence quantification analysis, and of course do a bit of more variability using the perception of the velocity of persons. And so there are lots of things to do, and applications, for example, quantifying skill of learning for persons doing surgical assessment, robot assisted surgery, fetal behavioral development as well, or nonlinear biomedical signal processing as well. It's plenty of things to do there. So the current work is about to be, I'm working on this mission, and I'm also going to put this into the archive. Just need to wait a few days to be approved. And thank you very much, and get in touch. All these slides will be in this repository if someone is interested.
Okay, thank you, Miguel. Very nice presentation. We have now time for questions. We have already one from the audience. Nina is asking you, when do you recommend to use nonlinear analysis tools? She is aiming to separate different sources of variability underlying behavioral variability, separate motor noise from exploration variability?
Okay. Yeah, that's very interesting question. Yeah, I guess all depends on the type of variability they want to use. I guess the first test to do is check, like how good are these different tools from each of these different activities, and then see how reliable your tools can quantify the differences between the source of variability. Yeah, but of course I can forward some papers, or maybe we can further this discussion, because I'm interested also in applying these tools. Like been playing around, and that will also be interested for you.